Hi, my name is Abou-Chakra, and I'm excited to present to you our work, ParticleNeRF. Applications like robotics are often looking for representations that can capture the state of the physical world. Desirable properties of such a representation include the ability to capture 3D structure and the ability to rapidly update in response to changes in the environment. This second property can be referred to as the online challenge and can be expressed functionally as follows. Given a learned representation R and new observations O, we wish to compute an updated R as quickly as possible. Over the past few years, NeRFs have emerged as a novel and powerful tool that can capture 3D structure from posed images. Despite their success at capturing 3D structure, investigating NeRFs as a plausible representation for a dynamic physical world has received little attention. This is mainly due to the absence of a fast NeRF formulation that is designed both to operate in an online manner and in a dynamic setting. Our work, ParticleNeRF, seeks to address this gap, and it does this by creating a NeRF that is architected to adapt to changes in the scene at interactive rates. A brief explanation of what NeRFs are will help frame ParticleNeRF's contributions. Neural radiance fields create a model of the world where each point in space is associated with a radiance value and a density value. To render the world from a particular viewpoint, rays are cast through each pixel of the image plane. Then, points are sampled along the rays and the radiance and density values are computed. Finally, the radiance and densities of the sampled points are reduced into the pixel colors. This process is differentiable, and given multiple ground truth images, taken from known poses, the radiance and density fields can be learned in such a way that realistic images and accurate depth maps can be rendered from viewpoints that were not part of the original training data. Different NeRF methods can often be distinguished by the manner in which they map between points in space to radiance values. This map is often split into two components. The first component, referred to as the encoding, maps a 3D coordinate to a feature space of arbitrary dimensions. It is this part of the formulation that is often different between various NeRF architectures. The second component maps the feature from the encoding layer to radiance and density values. The choice of encoding has a large effect on the speed at which a NeRF is learned. ParticleNeRF's contribution is in part a new encoding that is designed to quickly update the radiance field when motion occurs. To observe the problem the online challenge presents to current encodings, consider a radiance field that has already been trained on a scene. We will consider how two candidate encodings for the online setting behave when an object within the scene begins to move. The first encoding we use is known as InstantNGP. This encoding divides the world into a grid and associates with each corner of a feature of a predetermined dimension. Querying the radiance of an arbitrary point in space is a matter of interpolating the features from the surrounding corners and mapping the interpolated feature into a radiance and density value using a neural network. As the object moves, the features associated with the corners need to be unlearned at certain locations and relearned at others. Although InstantNGP is designed for static scenes, it is extremely fast and well optimized, and is therefore a valid brute force strategy that could potentially work in an online setting. In contrast, the second encoding we consider is known as time-aware neural voxels, and it is designed to learn dynamic scenes, albeit in an offline manner. The TNV encoding is part of a body of work that seeks to capture 3D video. We adapt this encoding to operate in an online setting. Methods like TNV utilize the concept of a canonical space. As time changes and objects move, the query points along a ray at a certain time are first morphed into the coordinate system of the canonical space. This morphing is usually done by a time-conditioned neural network, named a deformation network. The strategy of bending rays removes the need to learn and unlearn features when movement occurs. Instead, tracking movement is primarily done by learning the appropriate time-conditioned deformation network. Time-aware neural voxels is one of the fastest methods that implement this strategy and is therefore a plausible candidate that could be ported to the online setting. ParticleNeRF's main insight is that when movement occurs in the scene, it is easier for the learned features to move rather than to relearn. To facilitate this, instead of associating features with a locked, regular grid, we instead associate them with particles in space. The positions of the particles are optimized together with the associated features. To query the encoding at an arbitrary coordinate, features from the neighboring particles are collected. Those features are then weighted by a Gaussian that decays with distance. The weighted features are then summed together. The resulting interpolated feature is given to a neural network from which radiance and density values are computed. Because the queried feature depends on the distance of the particles and not their explicit coordinates, a collection of particles that is translated or rotated will continue to represent the same geometry. The particles in our encoding are also associated with a velocity, and they are acted upon by a particle-based physics system that is responsible for all particle movements. When the gradients of the reconstruction loss relative to the particle positions are calculated, they are interpreted as velocity impulses, which are ultimately resolved by a physics loop. The physics system also provides a means with which we can add physical priors directly to the particles. In ParticleNeRF, we add a collision constraint that gives particles a physicality and removes the possibility of multiple particles occupying the same space. Our results show that ParticleNeRF is capable of learning a 3D scene and that the particles tend to follow an object as it moves. In this scene, an object is being observed by 10 cameras. The particle encoding is continuously being trained on the observed images. We continuously render both the particles and the 3D scene they are representing. As we manually move the object, the particles rapidly follow the geometry and maintain an accurate reconstruction. We jointly optimize the features associated with the particles as well as their positions. To qualitatively observe the effect of allowing the particles to move, we show a scene of a wheel rotating at successively faster speeds. InstantNGP's grid-based encoding fails to learn and unlearn features fast enough to keep up with the rotation. Similarly, when the particles are locked in place, the reconstruction quality drops immediately after motion begins. If the particles are allowed to move without adjusting the associated features, reconstruction quality significantly improves but exhibits a gradual decay as minor errors accrue over time. When both the positions and the features of the particles are optimized, the reconstruction quality remains accurate for a much longer period. Time-aware neural voxels is more resilient than InstantNGP to the online setting. However, it fails on larger motions. We attribute this to the absence of a motion model within TNV's formulation. If an object is moving at a certain speed, the physics system within our encoding endows the particles with momentum that brings them closer to their ideal locations at the next time step. TNV's deformation network, however, has no explicit concept of velocity and is therefore not as well suited to guessing the deformation that will occur at the next time step. Our full evaluation is run on a set of scenes that incorporate deformable motion, rigid motion, and articulated motion. We use images from 20 cameras to continuously train each encoding. At every time step, we evaluate photometric reconstruction metrics from 7 novel viewpoints. We show that ParticleNeRF is consistently better at maintaining the accuracy of the learned scene in the online use case. In summary, ParticleNeRF is the first encoding that is designed specifically to operate in an online manner on dynamic scenes. It does this by coupling features to particles that are free to move and follow dynamic elements. The motion of the particles is governed by a physics system that endows them with both a motion model and a principled means of restricting unwanted configurations. This formulation allows NeRFs to rapidly update to changes in the scene and is therefore a stepping stone towards their active use in time-sensitive applications.